Let's continue in 14.3. We want to look at now the geometric interpretation of the first partials. So partial of f with respect to x, partial of f with respect to y. So let's go ahead and draw this diagram. This is my generic surface. So you draw this surface like this, okay? So it can be defined, the surface, in terms of f of x, y, and then we call it usually surface S or something. It doesn't matter right now. Okay, so the function, the surface is like, picture like an upside down parabola maybe, but that's what that generic surface is. So you have this generic surface, looks like this. And then we're going to look at, so that's what we're going to say, let S be the graph of z equal to f of x, y. So we will call that graph S. Which I don't think I wrote that anywhere. Okay, so we'll call that graph S. And it's defined by f of x, y. Okay, then, let's write this down. The slope of the tangent line L at AB, okay, so here's A, and here's B, and you go up to the graph, like this. So this point up here is f of AB. So the slope of the tangent line L1, so here's L1, let's picture that being tangent, like that, at the point along the plane x equals a. So that's the y direction. So picture a plane right here cutting up through and making that cut right there. Okay, so that's x equals a. I know it's hard to draw it, but basically that's your x equals a. Picture it going up and cutting through that surface. Is given by partial of f with respect to y. And I noticed the colors here. Actually, I should have changed that color. Okay, so partial of f with respect to y. Don't look at the colors. So partial of f with respect to y is the slope of the tangent line in the y direction. Right here. This is the y direction. And then, similarly, partial f with respect to x is the slope of the line L2. So here's L2, and this is going in the x direction. So that's what I want you to remember, is that the partial y is in the y direction. Makes sense, right? And then partial f is in the, partial x, fx, is in the x direction right here. So it's the slope of those, so it's in those directions only when you do those first partials. And then this line x equals b, it would be this plane that goes and cuts up through to make that curve right there. Okay, so that's the geometric interpretation. I'm just showing you what it is. I'm not defining it with the limits and all that. But basically, you're fixing a value of x, and then everything else is the same. It's like you create this plane that cuts up through right here and here, and then you're like in a plane. So you're doing the same exact thing that you would do in single variable. Okay, so write this down to partial f with respect to x gives the slope in the y direction, which that's how you remember it. Don't worry about the whole plane thing. It kind of throws you off at first. Partial f with respect to y gives the slope in the y direction. So that's what you remember. All right, so let's look at an example. So basically try this one. It's pretty easy, relatively speaking, of course. Find the slope of the tangent lines at 0, 0, 1, excuse me, of z equal to e to the negative x cosine y. So basically take each partial and plug in your values. Okay, so what I like to do sometimes too is like, does this value satisfy this thing? Does that work? So this is x, y, z. So z1, if you plug in those values, and let's see, e to the 0 is 1, cosine of 0 is 1. So yes, it works. I mean, it has to work. I mean, I gave you the problem, but that's something you want to think about. Does this actually satisfy this? And it does. Okay, so take your part, so try it. I'll do my little thing again, so try it. So take your partials, partial zx, partial zy. All right, so zx, you're taking the derivative of e to the negative x, and cosine y is constant. So it's just negative e to the negative x cosine y. And then let's evaluate using the evaluation bar at 0, 0, 1. And really you just put in x, y, you put in 0, 0. So that's going to be negative 1. Now let's do the partial z with respect to y. And it's negative. Oh, yeah, derivative of cosine is negative sine. So negative e to the negative x sine y. And then let's evaluate at the same point, 0, 0, 1. And that is, of course, 0, because sine of 0 is 0. So the slope of the tangent line in one direction is negative y. Slope of the tangent line in the other direction is 0. Okay, next thing is changing gears a little bit. This is basically the definition of differentiability. Let's take a look at that. And I have a supplement for this. I will give you the supplement online. So this is the definition of differentiability. So this is basically, how do we know a function z of f of x, y is differentiable? So, well, this is actually defining it, and then we'll talk about it. Okay, so a function given by z equal to f of x, y is differentiable at a point x naught, y naught if delta z can be expressed in this form, can be expressed in the form delta z equals partial f with respect to x of x naught, y naught times delta x plus partial f with respect to y of x naught, y naught times delta y plus epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1 and epsilon 2 both approach 0 as delta x, delta y both approach 0. And then it's differentiable on a region. So I'll just say differentiable on a region R if that's true for all x naught, y naught in R. Same kind of thing we've done in the past. Okay, so note or recall, delta z is defined to be your f of x plus delta x, y plus delta y. minus f of xy. So you're incrementing on your delta x both variables. You're incrementing on x and y when you say delta z. So basically you want to make this look like this when you show something's differentiable, and that's what we're going to do. Okay, so this is what I want us to be able to do, is use the definition of differentiability to show f is differentiable. So let's take a look at this. Show a function is differentiable. Okay, so show that f of xy equal to y squared plus 4x is differentiable at every point in the xy plane. Okay, and then I'll state this more clearly, but basically by the definition. So by the definition, show it. So this is what we want to be able to do. Oh, and this is not very well stated in the book. This is one of the other only things I'm going to have you do separate from the book, and I'll give you supplements. So what you do is you start with your delta z like this and expand it out to this form and see if you can identify your partial fx, your partial fy, epsilon 1, epsilon 2, and you rearrange. So watch how this is done. So to get started, to show this is true for every point in the plane, we want to place those in the plane. So first we're going to say let xy be in R2. So we're going to basically assume that xy is any point in the plane. It's arbitrary in the plane. So then everything we do is in the plane. All right, so you start off with delta z. So delta z is, I'll write this out, so it's f of x plus delta x, y plus delta y, minus f of xy. And then that's what we substitute in. This could get really messy fast if it's not a simple expression, but you basically get y plus delta y squared plus 4 times x plus delta x, and then minus the function, which is y squared plus 4x. Now, before you continue expanding and stuff, we want to maybe look at what is partial f with respect to x, because that's part of what we're trying to show. We're trying to find those. So partial f with respect to x is just going to be what? And that's just going to be 4, and then partial fy, what'll that be? That's just 2y, yeah. Okay, then when we expand this out, we're going to look for partial fx, partial fy in this expansion. So let's multiply it out, simplify it. Okay, so that's equal to, where am I at? Okay, so that's y squared plus 2y delta y plus delta y squared. And you treat the delta y as like one variable. It's like smashed together. You don't have to put parentheses and stuff. And then plus 4x plus 4 delta x minus y squared minus 4x. And so let's go around and simplify it. Let's see, we get y, negative y. We get positive 4x, negative 4x. Those are all gone. And then let's start looking for how to rearrange it and place it in this form. So do you see a 4 delta x somewhere? Oh, it's right there. Check that out. Do you see a, let's see, what was partial y? 2y? Do you see a 2y delta y somewhere? Oh, look, right there. Yeah, so that's how you can rewrite it. So you rewrite that then as 4 delta x plus 2y delta y plus, and this is where it gets a little interesting. There isn't a delta x term. There isn't an epsilon 1 delta x term. So you just put it in. 0 times delta x plus, and then we have what? Delta y squared. So that's delta y, delta y. So what that means then is you get, so that's your epsilon 1, that's your epsilon 2, and then these are your partials. There's your partial here, and one more, and there's your partial here. So it's exactly that form above. If you have to, like this, you force it to be that form above. So then you state what they are. Then you say where epsilon 1 equals 0 and epsilon 2 equals delta y. And they both go to 0, and then you finish the statement. And epsilon 1, epsilon 2 both approach 0. One's already 0, like duh. As delta x and delta y both approach 0. Okay, so then you can conclude if you'd like. Therefore, f is differentiable at every point in the xy plane. Okay, so this next example, try on your own. I don't have it written up, so you can just try it. We can look at it later if you want. So show that f of xy equal to x squared minus 3y is differentiable on the xy plane. At every point in the xy plane is how you can say it. Okay, so a couple more things to do. Next theorem. So next theorem, and we will prove this one too. This one's a nice one. So basically this one says differentiability implies continuity. So if f, and the converse is not true, just like Calc 1. So if f of xy is differentiable at a point, so at x naught, y naught, then it is continuous at that point. And then if you want to make it everywhere, like in a region, then you just set that arbitrary in the region. Okay, so differentiability implies continuity. So that's when you get a function like that. However, continuity does not imply differentiability. Here's your counterexample. Okay, so differentiable, basically you get nice smooth function, and it's continuous. Continuity, this is continuous, but it goes to a cusp, and therefore it is not differentiable at whatever this point is. Okay, so this is the differentiability implies continuity, but continuity does not imply differentiability. So it's not differentiable here, whatever value that is. So you could have a corner or a cusp, and it's not differentiable. Okay, let's look at that proof using the same technique as above, actually, because that's what the definition is saying. Right, so if it's differentiable, we get all this stuff. So differentiability implies all this. Well, we get all this. Continuity is what we said earlier in the previous meeting or lecture, and that is the limit value equals the function value. So basically, we're going to use this idea. So this is how we're going to prove it. So the idea to prove it is we're going to use limit of f of x as x approaches a equals f of a. Okay, so that's that's what we want to have. We need that to be continuous. So that's true. So this is there's a theorem basically that says if you can show this and f of a is defined and real, then, or a real number, then the function is continuous. So that's equivalent to saying basically this. So it's equivalent to saying the limit of f of x minus f of a as x approaches a equals 0. And we'll be using that doing that in two variables, but same idea. Okay, so we're going to use that concept. So here's the proof. All right, so let delta x and delta y be those same increments as above. So we say be increments. And we have to say or state, assume f is differentiable at x naught, y naught. Okay. So then we have two things. One, delta z is equal to, by definition, f of x naught plus delta x, and then y naught plus delta y, minus f of x naught, y naught. Okay? And then two, since f is differentiable, we get this from above. We get delta z can be expressed in this form, partial fx of x naught, y naught, delta x, plus partial fy of x naught, y naught, delta y, plus epsilon 1 delta x plus epsilon 2 delta y. That's what we get, basically, by definition of delta z, and by definition of differentiability. We get this. Okay, going to rearrange the top a bit, or two a bit. I meant to say two. So partial fx of x naught, y naught, plus epsilon 1. You can rewrite that and factor out your delta x, plus partial fy of x naught, y naught, plus epsilon 2. And you factor out your delta y. And this is the step that, can be a little confusing, not confusing, but we're going to use what delta x is. So we're going to let x equal x naught plus delta x. Is kind of clean it up a little bit. so that delta x is x minus x naught. And then we're going to let y be y naught plus delta y, so that we can write delta y is equal to y minus y naught. So the reason we can do that is we're basically saying it's a variable. Well, you're at a fixed value or fixed point, but then you're incrementing by delta x. So it varies. So this delta x means that it varies, so that you're not fixed at x naught. So that's why you can let it be a variable. Same thing for y. Okay, then substitute, and we end up with this form. We end up with f of x, y. This is long. You're going to go all the way to the side. Minus f of x naught, y naught. So that difference, I'm just taking the difference because that's what I need to do eventually, is equal to all of this, partial fx, x naught, y naught, plus epsilon 1. And then this is x minus x naught. And then plus partial fy of x naught, y naught, plus epsilon 2. And then that's y minus y naught from above. I'm just substituting in there, but now what I'm going to do is take the limit as x approaches x naught and y approaches y naught. When that happens, and when you do that, these both go to 0. If those both go to 0, this whole thing goes to 0, and then this difference equals 0. So that's basically it. Okay, so now take the limit on both sides as x, y both approach x naught, y naught. Okay, so then when you do that, you get the limit of f of x, y minus f of x naught, y naught as x, y approaches x naught, y naught equals 0. Again, it's this you're taking a limit of, which means these are approaching each other, so those both go to 0. So I like to actually write that in there. So what you're getting then, let's use that color. So these are both going to 0 when you take that limit. Okay, so think about that. Doesn't matter what these are. These are going to 0. So we can rewrite it like this because we're assuming it's differentiable. So very powerful stuff there. Therefore, f is continuous. So if you get this form, we know f is continuous. Okay, so that's just like we did above. So therefore, limited and f is continuous. Okay, next theorem is so you don't have to like show that every time. There's actually a nice simple theorem that shows this, not without proof. This is called sufficient conditions for differentiability. It's pretty easy actually. So this is sufficient conditions for differentiability. Basically, says if partial fx, partial f, and partial fy are continuous, like exist and are continuous, then f of xy is differentiable. Which kind of makes sense, right? I mean, that's what we're trying to do anyway. So that's really all you have to do is if you do the partials and they're continuous, then it's continuous, it's differentiable everywhere they're continuous. So basically, f is differentiable everywhere partial f xy are continuous. So maybe not differentiable, like, there could be a cusp or something like that. Okay. Let's see. I think that's it. That's all of 14.3. 14.4 is next, the chain rule. That's some fun stuff there. A lot of different stuff going on there. 14.5, directional derivatives and gradients. That'll be interesting. Good stuff there. 14.6, tangent lines and planes to surfaces. I'm just going to use all this stuff in here. 14.7, extreme values. So this is when you get to like max and mins of curves. There's a lot of stuff in this chapter. And there's one more, isn't there? 14.8. 14.8 is Lagrange multipliers. That's a trip. Okay. See you next time.